I have given you a final tree on how machine learning, what are the categories of machine learning and what kind of techniques you can use. So here you can see broadly there are three categories. One is four categories: regression, classification, clustering, and dimensionality reduction. Dimensionality reduction, there is only one technique called PCA. Clustering is also very simple. It's very easy to understand. Uh, so the only remaining thing we have to focus more on, we will definitely focus on regression and the clustering and dimensionality reduction. But the most important thing we'll focus on is the classification thing, because this is the most widely used technique in the market. Because any business decisions that you want to take is definitely from the classification. It's never from the, it is rarely that you will use clustering. uh, Dimensionality reduction is also part of one of the classification problems. So if you have a classification problem and you have a lot of variables, you do the dimensionality reduction first and then do the classification. That's how we do generally, or any regression also. Just before applying the regression, use the dimensionality reduction and then apply regression. That's how we generally do. So the final techniques for taking any business decision will be either regression or classification. So let me open another page. So let's today talk about GLM. This is called generalized linear models. So generalized linear models, it's a extension of the linear regression, so that we can use any kind of y variable. So if you remember the regression assumptions, so one is expectation of the epsilon, which means errors equal to 0, and variance of epsilon is going to be sigma square, and covariance between EI and EJ is going to be 0. And finally, errors follow normal distribution with 0 and sigma square as the mean and variance. So this is how actually we define the linear regression. Let me write it as assumptions of linear regression. Now the question is, what if errors doesn't follow normal? Linear regression. So if errors doesn't follow normal distribution, actually our y hat is nothing but x beta hat, and y can be written as y hat, which is the predicted value, plus some error. This is how we got the errors. If errors are normal, then y is also normal. That is the reason why we are checking for the normality of the errors. We are not checking for the normality of the y, but indirectly we are checking that by checking the normality of the epsilon. If errors are normal, we are adding errors to some variable, some normal distribution variable to some other variable. That will finally get you another normal distribution, which means if errors are normal, regardless of this distribution, the final value by adding the y hat, which is y, will also become normal. Then y is also normal. So, which means in our data set, if we have y, x1, x2, x3, x4, which is our cement data set, if you remember. In this data set, some y1 or let me say 5 or 50, 5.1, 2.6, 3.4 and 2.8. Let's say these are the chemical composition in percentage. And this is the heat that is evolved. This is what is the data set I have shown you. So if the errors are normal, it means that this entire column, which is y, is also normal. If epsilon is normal, then y is also normal. Okay, this column is normal. But what happens if epsilon is not normal? If epsilon is not normal, we anyway do not have any guarantees of the distribution of y hat, which means y will not be normal anymore. So this is the question that needs answering in GLM. GLM only discuss about what if y is not normal? What if it is something else? So what we are doing is we are generalizing the assumptions of the assumptions of the linear regression so that y can be any distribution other than normal. It can be normal also, it is fine. But what if it is not normal is the question that we want to answer. So GLM is a generalized model. It's much more generalized than what is linear regression. So GLM can be applied when y distribution is from a family of exponential distributions. Now, what is this exponential distributions? There are some kind of distributions which are called exponential family of distributions. So, for example, normal distribution by itself is an exponential family of distribution, which means our linear regression is a special case of generalized linear model. Linear regression is a special case of GLM. So that's how we can think of this one. And there are many more exponential family of distributions. Binomial is one more. Binomial distribution. Poisson distribution is also exponential family. Then negative binomial. I have not discussed this particular distribution, but it is just a reverse of binomial distribution, slightly changing. So there is a gamma distribution. All these are exponential family of distributions, which means you can take y as one of these distribution. For example, we already took y as normal distribution and it became linear regression. Now we can take binomial distribution, y as binomial distribution. Then the regression that we are going to do is called logistic regression. If we take y as Poisson distribution, y is a value from a Poisson distribution, then this is called Poisson distribution. Poisson regression. So this is how actually we take each of these distributions and convert it into some other regression format. So that is a use of generalized linear model. If y is not from the normal distribution and it is from one of the exponential family of distributions, then we use GLM, which is generalized linear models, to apply this kind of regression techniques. Any questions on this? Why we need this GLM?
Can you repeat the last sentence?
What is that you want to repeat? You want me to repeat?
Basically, the last sentence where you said why it is that we need the GLM.
Yeah. If y is not from one of the normal, I mean, if y is not from normal distribution, if y doesn't follow normal distribution, then what happens? Linear regression cannot be applied, because what is y? What is normal distribution? Normal distribution is one of the distributions of continuous variables. But let's say my variable is not continuous distribution. It is not from the continuous distribution. It is from the discrete distribution. If you remember, binomial, Poisson, these are discrete distributions. So if y is from some other distribution other than normal distribution, then I cannot directly apply linear regression. So what I do is I need some kind of a generalized way, so that regardless of any y distribution, I should be able to solve the problem. Just because y is not from the normal distribution, which means this assumption number 4 is wrong. If assumption number 4 is wrong, even assumption number 2 will also be wrong. Variance of epsilon is equal to sigma square. This will also be wrong, because epsilon is not following normal distribution. If epsilon is not following normal distribution with sigma square and sigma square as variance and 0 as the expected value, then even this one and this one will also not fall into, I mean, these two also will not work. So majority of the assumptions will be false, which means I cannot apply linear regression at all. So what I should do is I need to have a generalized way to define this kind of an assumptions. So in GLM, I don't care about any of these assumptions. In fact, I don't care about first assumption, which is expected value of epsilon equal to sigma square, expected variance of epsilon equal to sigma square, covariance of epsilon 1 and epsilon j, epsilon I and epsilon j equal to 0. All these assumptions are not validated in GLM. The only assumption that GLM has is GLM can be applied only when y is from one of the exponential family of distributions. The most important distributions that we will be looking at is normal distribution, binomial distribution. When you apply binomial distribution, the corresponding regression is called logistic regression. We'll be looking a little about Poisson distribution. Actually, this is not part of the syllabus, but we can look into the Poisson regression as well, to some extent, not much. So these are the most important regression methods using GLM. So the reason why we use GLM is when y is not from one of the when y is not from the normal distribution. This is linear regression. Is it clear, Vijay?
Yes, Sandeep.
Okay. Now, to understand what is this, how can we apply binomial distribution to regression, the existing whatever regression that you know of, or Poisson distribution, or any of the distributions? First, you need to understand if the distribution itself is from the exponential family of the family of distributions or not. That is the first thing. The second thing is, if it is from the exponential family of distributions, then how would I fit the model? So for that, I'm writing one statement. This is from a book called Draper and Smith. These are two guys who wrote that book. The book name is Applied Regression Analysis. Okay, this is one of the best books that I can suggest you on linear regression, applied regression analysis. So this is the book, Harry Smith and Norman Draper. So this book is one of the classic literature available in the market currently. If you are further interested to read about how regression can be applied and all those things, you can read this book. Most of the text or most of the subject that I have taught is mostly from this. Though I have not taken the entire subject because it is a very big course here. But you can see I talked about extra sum of squares, fitting the straight line equation. Of course, fitting the equation is very important. Multiple regression, multiple linear regression, R square. I did not talk about big Fs and all those things. Dummy variables, transformations. Okay, then ridge regression and GLM I am talking about right now. Ridge regression is something that I'll talk about later. So many of these things I have talked, but after this, I think geometry of least squares and all these things I did not talk. Non-linear estimation. These things I did not talk about and I will not talk about. Robust regression is also something I did not talk about. Resampling again we'll talk about further. So most of this book is covered actually, at least 90% maybe. So this is one of the best books available in the market, and I'm taking one of the statement from that book and I'm using it for understanding the GLM, the topic of GLM. So a random variable, this is an exact statement. So I'll talk about how we can apply this. Sorry, U of Y that belongs to the family of exponential distribution with a single parameter theta has a probability density function f of u comma theta equal to s of u into b of theta into e power au into b theta. Okay, so any exponential family of distribution should fall into this kind of a pattern where your parameter is theta here, Okay, and if your function is of the format f of u comma theta, the function has to be like this: s of u and b of theta into e power au and b theta. Now the question is, will all the distributions fall into this kind of this kind of format or not? So for example, let's see one example where it is not, which is binomial. Before that, actually you can see there are u and theta, those are two parameters, and I mentioned that here it is only single parameter. The reason is the other parameter we call it as nuisance parameter, which means we'll not consider that as a parameter at all. Let me define that. Nuisance parameter. The parameter that we are not interested in is called nuisance parameter. So here I do not care about u, I only care about theta. That's why I can call this probability density function as having only one parameter, because the other parameter is something that I don't care about. I'm not even interested. I'm not caring about the other parameter. So that kind of parameter is called nuisance parameter. First of all, let's see how does this all apply in binomial distribution. Okay, so here binomial distribution, the probability density function, can anyone tell about it? Do you remember it? I told you that I'll use it somewhere else, if you remember. NCR into p power r into 1 minus p power 1 minus r. Sorry, 1 minus p power n minus r. Okay, n minus r. So this is a this is the binomial distribution's probability density function. But if you compare it with this, you can see these are nowhere related. There is no e power, there is no s of u, s of b of theta. These kind of things are not there. So to convert this, you need to do something called something like logarithms. Let me show you how to do it. But before that, let me convert this into f of n comma r. These are the two parameters, n and r. One second, is it n and r? Yeah, it is p and r. P is the parameter that you will have, and r is another parameter you will have. So instead of using this, instead of p, I'm using u. Sorry, instead of p, I'm using theta. Instead of r, I'm using u. Similar to this one, theta, u comma theta. Or let me do that same thing. Let me call p as u, r as theta. This is nothing but nc theta into u power theta into 1 minus u power n minus theta. Okay, I'm just using the same format, u comma theta. Now the question is, I need some function of u, only u, but this is having both u and theta. So I need to convert this kind of a function into something else. So to understand that, let me talk about logarithms a bit and come back to this. Logarithms. Because I need something like e power something and all these things I need. So that is what I don't have. So if you see this e power something, this is having something of function u as well as function of theta. But here I have function of u and theta, but is not that is not e power that e power this function. So it is actually not in the form of this format. Are you clear or not? First of all, before I are you clear that this format and this format is completely different? I can call binomial distribution as exponential family of distributions only if this condition is satisfied. If the probability density function is of this format, that's what I mentioned here. The random variable will belong to the family of exponential distributions only if it is following this format. If it is not of this format, I don't care. I mean, I don't use this. I cannot use binomial distribution as GLM. I cannot use binomial distribution in GLM if it doesn't follow this format. Are you clear or not? Okay. So let's go into logarithms. Let's see how logarithms will help us convert a distribution of this format to something like this. And that is what I am interested in today now. So logarithms, what is this logarithm? Logarithm is nothing but it is an inverse of exponentiation. What is exponentiation? So for example, if I say y equal to x power 3, this kind of powers is nothing but exponentiation. The inverse of this exponentiation is nothing but logarithm. So how to do this inverse? So what I need is, if I apply logarithm on both the sides, every logarithm will have something called base. So logarithm of y base x is nothing but it will become 3. How did I get 3? One second, let me not confuse you. So logarithm of y base x, what it is saying is how much to the power of x is y, is what I am calculating here. So how much to the power of y, sorry, how much to the power of x is y, is what is my question. So if I apply logarithm of y base x, I should get 3. So what it means is x to the power of 3 is going to be y. So that's how we can do logarithms. Are you clear with this? How much to the power of x is y? So for example, tomorrow I can ask you, what is log of 16 base 2? So how much to the power of 2 is 16? Can anyone tell? What
2
is
power
this?
4.
2 power 4, right? So 4 is the answer. 2 to the power of 4 is going to be 16. So when you're applying any logarithms, we're asking for how much to the power of this value is going to be the other value. How much to the power of this value is going to be this value. So only 2 power 4 is going to be the answer. So similarly, if I ask you again, or let me write it as examples. So the first example I told is log 16 base 2 is 4. Again, log let's say base 3 of, let's say, 27. How much it is?
Three.
It is 3. Or let's say I say log 625 base 5. How much it is?
It's 25.
It is 4, right? How much is 5 power 4? 5 into 5 into 5 into 5. 625. Okay. It's a little tricky, right? But you can find it. It's not a difficult one. Okay.
What if we have log base of 5 of say 24 instead of 25?
Yeah. Log base 5 of 24.
Yes.
Actually, how much is 25? It is close to 2. So something less than 1. It is something 1 point something.
Okay.
Okay. It's a decimal value. I'm just giving the appropriate whole number so that it is easier for you to find. Decimal value, generally, if you want to do it, logarithm of let's say 24, generally this will be base of e, or let me see if it is which base it is. Yeah, this is a base 10. So log of 24 by log of 5 is what you are asking me. It is 1.97. Something that I cannot calculate by hand, but yeah, I can easily say that it is less than 2 and closer to 2. Okay. I'll tell you how I did this math. Okay. I did not tell about this math. I'll tell you. Now let's see, 1.97, right? This is something that we need to remember and come back to it. Just remember about it. I'll tell you how to calculate. How did I calculate using that calculator? Now, that is about the simple logarithms, but we need to know about the properties of the logarithms as well. So if there are two variables that are multiplied, log a into log b, log ab. If I need to multiply these two elements, what I can do is I can also separate them, log a and log b, and then just add them. Which means in logarithms, if you multiply two elements and if you apply a logarithm on top of it, you can just add the corresponding logarithms. Log ab is nothing but log a into log b. Let me write it as log ab. So log ab can be written as log a plus log b. Similarly, what happens to log of a by b? So it's almost similar, except that instead of plus, you have to use a minus. Log a minus log b. Okay, these are few properties of the logarithms. Let me write another property, which is log a base a. How much to the power of a is going to be again a? How much it is?
1.
1. And what happens of log 1 base of any x? Any variable in any base, you can use any base, but the power of x, any power of x that will become 1 is 0, because x power 0 is going to be 1, since x power 0 equal to 1. So Whenever you are getting something called log 1, just call it as 0. Then how to change the basis? Log a base b. If you want to write this logarithm using some other base, let's say I need to change this base from b to some c. What I have to do is log a base c by log b base c, which means I can convert logarithms of one base into another base. All I have to do is I have to take a logarithm of a with the new base. I have to take b, again take a logarithm of b with the new base, which means I am converting logarithm of one base into another. Now let's go back and see how I calculated this one. So every logarithm will have a base, which means whatever I did here is also having some base. So initially I tested how much is the base. So if you see, if I am getting 1, what does it mean? Log a base a is 1, which means for any value, if the logarithm value is 1, then that is a base that I'm getting for this logarithm, which means if log 10 equal to 1, which means how much is the base? The base is 10. For whichever a, the logarithm is 0, the logarithm is 1, that is the same base that I'm looking for. So here in Mac, whatever I'm getting is, it is a logarithm of base 10. Generally in this kind of calculators, you can also see ln. Ln generally is a base of e. I'll tell you what is e. E is a special number which is 2.718. It is some special number. Don't worry about what is the c. I assume that it is a special number. Now, if you want to do log 24 base 5, how to do it? Actually, whatever we are getting is log, if I say log 24, I am getting some value, but this value is not exactly the base of 5. What I am doing is log 24 base 10, if I do like this directly. But what I need to do is I need to change the base. How to change the base? Just like the way I told you just now. So log 24 base 5 is nothing but log 24 base 10 by log 5 base 10. If I do these two things and then just divide them, I'll get log 24 base 5. So that's why what I did is log 24 by log 5. If I do this, what I get is log 24 base 5. Are you clear, Vijay? How to do all these things? Now you can use any base. For example, the way that we did log 625 base 5, it is 4. Unfortunately, some mathematical error, but you can see it is very, very close to 4. It should be exactly 4. It looks like there is a problem in the the calculator. Or if you want log 27 base 3, again this is also close to 3, which is what I told you. And again log 16 base 2, this is also 4. Okay, that is how actually we can use the calculator, or let me use the proper calculator. Maybe you are getting confused. So you can see in any of the scientific calculators, I'm using the one in Mac. You can use any one, but you have to you should not use any basic calculator. Basic calculator will have only plus, minus, into, and all those things. Scientific calculator is what you generally should use. Okay. Here you can see log base 10. So once again, in any calculator you can use this. So for example, log 24 base 10 by log 5 base 10. If I do both of them, I should get the same answer. Instead of using all those confusing things, I just opened the calculator, nothing else. Okay, any questions on this? Okay. There are a few more properties. Logarithm of a power x base b. It can be written as, if there is a power in the value, what you can do is you can convert this into x into log a base b, which means this power comes as a multiplying factor, nothing else. Similarly, let's say log I think these are enough. I think this is enough. This is more than enough. We'll add to if there is anything else, but mostly these are the things that you generally need for logarithms. Any questions so far? Any questions?
Sandeep,
Yeah.
to go back to the definition, it's a little confusing, Sandeep.
Which one? The
Yeah, this one. Yeah.
this one I'm going to teach you. It's not done. I went to logarithms because I cannot convert this into this kind of format. I did not have the my original distribution. It's not exactly like this. There is no e power, there is no s of u, s of beta, b of theta. All these things are not there. That's why I went into something called logarithms, because that is what I am going to use to convert this binomial distribution into some format like this. Then I'll talk about it. Okay?
Okay.
For now, just think about it as a plain statement. Don't worry about it.
Okay. Okay, Sandeep. The reason I asked was I had to step out for a 5-minute call in the middle, so which I sort of lost the track when you're talking about applied regression analysis.
Okay. This is just a so this is a function that we need to have. This is the so any function, any probability density function that is of the format of s of u b of theta into e power au into b theta. Any probability density function that is of this format, I'll call it as an exponential family of distribution. That's what is this statement saying.
Okay.
Okay. Now the question is, I need to have exponential family of distribution to properly apply GLM. The only assumption left over in GLM is only it should be from the exponential family of distribution. I told you that these are exponential family of distribution, but I want to show it. How can I prove that this is an exponential distribution or this is this exponential distribution? So that I have taken from one textbook called Draper and Smith, Applied Regression Analysis. So that is the statement I am showing.
Okay.
But again, I gave you only the statement. I have to convert this kind of a binomial distribution thing into this kind of format. Only then I can prove that these two are same. This is a binomial is an exponential family of distribution. Okay.
Sandeep, just one more question.
Yeah.
In yesterday's class, you drew that tree structure.
Yeah.
Where you went into supervised, unsupervised. Then in unsupervised, you went into clustering, agglomerative, divisive, and all that. Where does GLM fit into that?
GLM is into classification.
into classification.
Logistic regression is GLM technique.
Okay,
Okay.
thanks.
We are talking about classification. Regression is done. I mean, we are going to go back into regression sometimes, but mostly it is done.
Okay.
Okay. Let me give you a break of 5 minutes. We'll come back at 7:26. Is everyone back?
Yes, Sandeep.
Others, are you back?
I'm back.
Okay, so just one correction. I made a mistake here. Sorry. I was thinking I did some mistake. I did not realize. So this is parameterized by R and P. And if you see, P is the most important parameter. R is something that I don't care about. So R is my nuisance parameter. P is the parameter that I am going to be interested in. So it's more like U and theta. R is U, which is the nuisance parameter. P is something that is I'm interested in. So in binomial distribution, the most important parameter is P, not the R. I'm sorry, I got confused. So this will become NCU. P is nothing but theta power R into 1 minus theta power n minus U. So this is a distribution of binomial. So what I'm doing here is using this binomial probability density function. What I'm going to do is I'm going to apply logarithm just to convert this into this kind of a format. I'll show you how to do it. So PDF is nothing but P of u comma theta equal to NCU into theta power u into 1 minus 1 minus theta power n minus u. Now what I'm doing is I'm applying a logarithm. Let me call it as f instead of n, all these things. So logarithm of this f is going to be logarithm of all these things together. Theta power u into 1 minus theta power n minus u. Generally, in mathematics, you use a base of e. In computer science, generally people use logarithm to the base of 2. But in mathematics, we are going to use base e. Anything is fine, but it's more of a convention. Now, what happens here is logarithm of NCU. These are all multiplication factors. If you remember, logarithm of AB is nothing but logarithm of A plus logarithm of B. Now that's what I'm trying to operate on. Logarithm of theta power u plus logarithm of 1 minus theta power n minus u. So what I'm going to do is I'm going to use another formula. Logarithm of a power x base b is nothing but x into logarithm of a base b. So these two parameters I'm going to use this formula. It is nothing but NCU plus u into logarithm of theta plus n minus u into logarithm of 1 minus theta. So then I'm using just plain mathematics. U log theta plus, here I can multiply this n minus u, which means n into logarithm of 1 minus theta plus minus u into logarithm of 1 minus theta. Now if I group similar items together, if I group by the u, these two can be grouped. Second term and fourth term, this term and this term, I can group. Logarithm of NCU plus u times of logarithm of theta by 1 minus theta. Sorry, or let me do it in 2 steps. That way you will get it. Logarithm of theta minus logarithm of 1 minus theta plus n into log of 1 minus theta. Now how to do it? Logarithm of NCU plus, if you remember this formula, log of a by b is nothing but log a minus log b. So I'm here, there is log a minus log b. I'm going to use this formula and convert it into log a by b. So this will become u into logarithm of theta by 1 minus theta plus n into logarithm of 1 minus theta. But on the right, on the left side, you have logarithm of f. But what we need is to understand if it is the exponential family or not. What we need to do is we need to get only f, not logarithm of f. So what I'm doing is, if log f is like this, f is nothing but e power, which is e or exponentiation of this entire thing, which is log NCU plus u into logarithm of theta by 1 minus theta plus n into logarithm of 1 minus theta. When I say exponentiation, actually e power all this value, all the value in the floor brackets. Now again, something to the power of a plus b, let's say. If this is the case, what you can do is you can write it as x power a into x power b. I can just multiply those terms. So similarly, I can multiply the terms here. E power log of NCU into e power u log theta by 1 minus theta into e power n log 1 minus theta. If you see this with the original definition that I have given you, what I need is, where did I write? S of u, which is a function of u, some function of theta into e power of some other function of u and theta, u multiplied with theta. Can I get this or not is what my question is. Some function of u, this is a pure function of u. It doesn't have theta at all. Some function of theta, here there is only theta, there is no u. And some function of u and theta, you have u as well as theta. Are you clear with this?
Yes, Sandeep.
Sorry?
Yes, Sandeep.
Oh, okay. I thought no, Sandeep. Okay. Okay, thank you. Any other questions? Others?
No, Sandeep.
Okay, and now this is not my interest actually. My interest is not showing binomial as exponential, is binomial an exponential distribution or not. If that is the case, I would have just said that Okay, just binomial distribution is an exponential distribution, just remember it. But I did not do that. The reason is because that is not really my interest. My interest is something else. Like, so my interest is how do I fit a model with y as a binomial distribution. If y is a binomial distribution, how would I fit the model? So to do that, I have converted all these things into some kind of a canonical form. This is called canonical form, so that I can find out what is the transformation on y I can do to make binomial distribution also look something like a linear regression. So I'm using some knowledge of linear regression, so that I can convert any binomial distribution y value into some kind of a linear regression kind of a formula that I am trying to find out. Okay, I'm trying to use that binomial distribution knowledge to convert it into linear regression format. So how to do that is my question actually. So before that, if you remember the earlier definition, f of u comma theta should be of the format s of u, which is this one. Then what did I say? S of u b of theta into e power au into b theta. Here if you so 1 second, is it au into b theta? It's not b theta. 1 second. Just give me 1 second. Let me write it in a different format. These two are not same. This is b theta. It should not be same here. So let me call it as c theta instead of b. This is a different function. I'm sorry for that. I don't know where I did a mistake. Maybe I did the mistake while copying it from the book. So what it means is s of u. What is s of u from this formula? This is from the binomial distribution. This is 1. From 1, what is from 1 and 2? Let me call it as 2. From 1 and 2, what is s of u? A function of u. It should contain only u, which means e power log ncu. E power log ncu. Okay, this is s of u. What is my b theta? B theta is e power log, sorry, this is not the one. E power n log 1 minus theta. Then finally au. Au is nothing but e power of something. So au equal to u actually here. So au equal to u and c theta. C theta is nothing but log of theta by 1 minus theta. Are you clear so far, or is it confusing?
How did you get u, Sandeep, for a of u?
A u, which one?
A of u, how did you get u?
So e power some function of u and some function of theta is what I'm looking at. Where did you get that? E power some function of u and some function of theta. That's why I compared these two. Now au equal to u, c theta is nothing but log of theta by 1 minus theta.
Correct. Okay, sir.
Sure, right?
Yeah.
Okay. Okay. From this, actually, I'm trying to find out what is the function I have to fit when y equal to y is a binomial distribution. Actually, when y is a normal distribution, I know that I have to fit y hat equal to x beta hat. This is what I have to fit when y is a normal distribution. That I know for sure. But what I did not know is how do I fit if y is not a normal distribution. That's why I went through all this pain. Okay. All this pain I went through only because I had to find out what is the function I have to fit. Now, let me write one more statement from the same book. If au equal to u, then f of u comma theta is in canonical form, and we need to fit the regression between c theta and x values, which means what is c theta? Log of theta by 1 minus theta. So log of theta by 1 minus theta is my new y hat. Actually, I should fit with between y hat and x beta. But now what I'm saying is, instead of fitting with y hat is nothing but the average line, this line. Instead of fitting with this line, I should fit with something called logarithm of theta by 1 minus theta, which means
Sandeep, not clear about the relation to regression, Sandeep.
yeah, I'll tell you. Theta by 1 minus theta equal to x beta. Actually, what is the linear regression line that I need to fit? Y hat equal to x beta.
Yeah.
Or let me not talk about x beta in matrix form. Let me talk about beta naught plus beta 1 into x1, beta 2 into x2. This is the equation I am going to fit. So on into x beta and xn. What is?
But isn't that continuous? Isn't that a function?
Yeah, that's what I'm saying. Actually, I should be fitting with this. Actually, I should be fitting with this, but I cannot do it because it is a continuous variable.
Right.
But instead, what I'm doing is, instead of using this y hat, I'm using this logarithm of theta by 1 minus theta. And on the right side, it is the same. What is changing here? Y is changing. So I am transforming y into something else. Okay. Actually, y is a different distribution than what I expected. I expected normal distribution, but it is not really a normal distribution. What I'm doing is, instead of using a simple y hat, I'm using some transformation. That transformation I'm calling it as log of theta by 1 minus theta according to this statement. What is this statement doing? If au equal to u, is it au equal to u? Yes. Then this function, this f of u comma theta, is converted into canonical form. Then if the function is in canonical form, then we need to fit the regression line between c theta, which is this one, and x values. Now I'll talk about c theta more. Don't worry about what is this theta and all those things. Don't put all those things in your brain. Leave that.
Maybe I was trying to understand in regression, it was a simple equation. We do not talk about probability distribution in regression. I'm trying to link the.
I will link that. I will link that. Okay.
Okay.
What if? So I did not talk about GLM at that time. I did not show you that there is a bigger picture where there is a generalized models for all the different distributions.
Okay.
All I told you is y should be normal. I did not explain that also properly. I did not tell why is epsilon normal. I only told you epsilon is normal. If epsilon is normal, then y is also normal. Why is that? Because y is nothing but y hat plus e. If e is normal, this epsilon is normal, then y is also normal. That's what I told you in the beginning of today's class.
Yeah.
So, which means this assumption indirectly is stating me that y is normal, y should follow normal distribution. But I did not explain you why y should be normal. Why can't it be binomial? Why can't it be something else? That I did not discuss at all. It is only now I am talking about, right?
Okay, sir.
I just showed you how to validate this assumption. This assumption, how to validate, I have shown you clearly. But why should I validate that? Or why should I have some epsilon which should be following normal? This is something like an error. If this is an error, why should I care about if the error is normal or if it is a Poisson or whatever it is? That I did not talk about at any point till now. Only now I am talking about, right?
Yes. But you spoke normal distribution in the context of errors, but not in context of y.
Yeah, because I did not show you all those things at that time.
Okay.
Because that is not the right time to show it.
Okay. Sir.
Only now I am showing what happens if it is binomial. Now, if it is a binomial, instead of fitting it with some y hat is what? Y hat is an average value actually. Yes or no? If you have data like this, where does your line fall in? It falls in exactly the middle. Why does it fall in the middle? Because for every x value, it is trying to find out the average value and trying to fit a line around that average values. When y is continuous and normal, when y is normal distribution. Now I don't have normal distribution anymore. All I have is a binomial distribution. An yes or no kind of question. Binomial is what? What is a binomial distribution? Binomial is something that will answer yes or no questions or success or failure. Right? It only has probabilities. Probability of being a success, probability of being a failure. It only have successful or failure probabilities.
Yeah.
Yes or no?
Yes, Sandeep.
Now, using that probabilities, how would I find? So, for example, if I plot, let's say 0 is having a cancer, 1 is not having cancer, and you are done with some blood test. Okay. Now, when you are undergoing some test through the blood, each of these x variables, for example, this is hemoglobin content. This is the number of red blood cells that you have, number of white blood cells you have. Each x variable, let's say it is a number which is representing one characteristic of your blood. Now, if I plot 0 and having cancer or not as 0 and 1, what happens is your variables will be plotted like this. If you do a scatter plot, your values will be like this. Why? Because if your red blood cell count is very less, maybe you are having if your red blood cells is high, then maybe you are having cancer. You are not having cancer. if your red blood cell count is very less, which means you are having cancer. Something like this. Yes or no? And it is discrete. There is no continuity in the line. After this, immediately it jumped on to this one. But earlier, if you see your plots, all your plots are like this, scatter plots, somewhat like this. It may not be exactly like this, but somewhat continuous data. Here there is no continuity. Suddenly, because your count is very less, actually instead of saying less, white blood cell count, if it is more, generally you'll have some problems in your health. So this side actually X is more, okay, X increases. So if your white blood cell count is increasing, what happens? Until some moment, your white blood cell count is okay. So which means you do not have any cancer. Once your white blood cell count is more, suddenly from here to here it jumps. Are you clear or not?
Yes, Sandeep.
So there is no continuity in the data. Now the question is, how would you fit a regression line between this kind of a non-continuous data? That is the problem we are solving actually. That is the reason why binomial is called discrete, because there will not be any continuity in the scatter plot. If you just plot a scatter plot like this, you'll not see any continuity. You'll just see discreteness like this. Now I need to find a regression line. How would I find? That is the question I need answering. Okay. That is the reason I went through all these things.
Yeah.
If not, I can directly fit a simple regression line like this.
Yeah.
Okay. Now what is this theta? Actually, if you go back, where did I keep it? 1 second. Yeah, I think even before this. If you see what is theta, theta is nothing but P, where theta equal to P, right? I just replace theta with P. Just to convert it to that AU B theta format, I'm using this. And U is nothing but R, right? NCR, instead of NCR, I'm using NCU. Instead of P power R, I'm using, I'm sorry, theta power U, okay? Instead of P power R, I'm using theta power U. So P is nothing but theta, which means I have to fit a regression line between, what is my final regression? P by 1 minus P equal to beta naught plus beta 1 into x1 plus beta 2 into x2 plus so on. Okay, so on into beta n xn. This is base E. Okay, I can call this right side as x beta in matrix format. Yes or no?
Yes, Sandeep.
So log of P by 1 minus P is nothing but x beta. Now if I solve for P, P is the probability, right? Probability of success. That's what I told in binomial distribution. Now if I solve for P, P by 1 minus P is nothing but e power x beta, which means P is nothing but e power x beta by 1 plus e power x beta. This is another format that another thing that you need to remember. And if you divide numerator and denominator by e power x beta, what happens? E power x beta by e power x beta by 1 by e power x beta by e power x beta. Numerator and denominator I am dividing by e power x beta. What happens? This will become 1 by what happens? 1 by e power x beta, which means e power minus x beta, and e power x beta by e power x beta, which is 1. Which means another format I can use this p is 1 by 1 plus e power minus x beta. Okay, these are some formulas that you need to remember. The significance of this formula is this function 1 by 1 plus e power x beta. This function is called sigmoid function. It's just a name of the function. Don't worry about the function name, but you need to know it. Sigmoid function is nothing but it is a S-shaped function, which means, and sigmoid is equal to 1 by 1 plus e power minus x. This x can be anything. Here in regression, I'm using x beta as a x. Okay, 1 by 1 plus e power minus x. What is this S-shaped function is? You'll have this function as, sorry, this function will be looking like something like this. In fact, I have already shown you how to draw this, standard functions. I have not shared you, sorry for that. But I'll share it immediately after the class. Sorry for that continuous disturbance I'm giving you. So if you see, I have plotted already the sigmoid function. Sigmoid is nothing but I have already defined as 1 by 1 plus e power minus x. That's what I'm telling you about the sigmoid function. If you plot this, it will be something like an S. Okay, and it starts from 0. If you see here, it starts from 0. It goes until 1. Now, if you consider this with this kind of data where 1 is not having cancer, 1 is having cancer, and 0 is not having cancer, if you plot an S-shaped function here, you'll get something like this. Okay, which means this function can be used to predict the probabilities. That's what I'm trying to say about this P. P is nothing but it is trying to predict the probabilities. And the probabilities always start from 0 and it ends at 1. That's why this function is very much useful in probability prediction, because it always starts from 0, it ends with 1. And also the probability is almost constant initially. Initially it is almost constant, then it starts increasing. Then after it reaches some confidence level, it starts stabilizing, which means the probability of having a cancer, there is some uncertainty in between, which means you're having some problem in your blood report, which means you're having some uncertainty here, maybe some 0.4%, 0.5%, or 40% chance, 50% chance you are having at some point because of the uncertainty in your blood test. But after some tests, if your blood is showing clear patterns, it means that you're clearly having the cancer, which means the probability is stabilizing at 1. At some point, if your blood is showing some clear patterns in having cancer, definitely you will have very close relationship and it will be very near to 1. This kind of S-shaped curve is called sigmoid function. There is another S-shaped function very similar to this. It is called tan H function. But if you see, it starts from -1 and +1. It's not really very useful in predicting probabilities, at least. For probabilities, this is the best function you can have, at least as of my knowledge. So that is about the sigmoid function that we are going to use. We'll go into detail, but for now I'm just showing how this sigmoid function is useful. Any questions? Any questions on the sigmoid function? Tan H is also very similar, but generally we don't use. We use only in neural networks, not here. Any questions?
No, sir.
No, Sandeep.
Okay. So that's all I have for today. We'll catch up tomorrow and understand how to fit this model. So today I have just shown you how binomial distribution can be used in the linear regression equation, which is log p by 1 minus p equal to x beta. So these two are having linear relationship, so you can fit a straight line equation. So if you see, log p by 1 minus p and x beta are having linear relationship, but p and x are having exponential relationship. These two are having different relationship. So that is a logistic regression. We're going to fit a regression equation. The other thing, if you remember, last time what we did is on regression, we tried to minimize the errors, squared errors. Here also we have to minimize or maximize something to find the best betas. We cannot find any other betas except best betas. So again, we have to find out what is the best beta here. So for that, we'll go into further analysis about the best beta. Once we get a best beta, first we need to understand how to get the best beta. Once we get a best beta, we are done with the logistic regression. We're going to look into the some problem. Okay.
Okay.
Okay. Okay. That's all I have for today. We'll catch up tomorrow then. Bye.
Thanks, Sandeep.
Yeah. Thank you. Bye.